Hello there and welcome to the Celestographer channel. Tonight, we are confronting a distance that sounds almost harmless, 1 light year. In astronomy, it is barely a step beyond home. For anything humanity has ever built, it is a wall of time, energy, and survival. Speed alone will not be enough. A machine must accelerate without carrying impossible amounts of fuel, endure years beyond repair, protect itself from what appears to be empty space, and still remain capable of doing something useful when it arrives. For human passengers, the challenge becomes even deeper. The spacecraft must provide air, water, food, protection, and a reason to keep going when Earth has become only a distant point behind them. None of this is clearly forbidden by physics. That may be the most unsettling part. The crossing sits somewhere between what nature allows and what human engineering can actually survive. Subscribe to the Celestographer on YouTube for more calm explorations of the universe, the machines we build to understand it, and the limits waiting beyond the edge of familiar space. Because crossing 1 light year would not simply require a faster spacecraft. It would require humanity to build something unlike anything that has ever existed. A passenger jet crosses a continent in hours, an orbiting spacecraft circles Earth in roughly 90 minutes, and a pulse of light could circle the planet about 7.5 times in a single second. Place those 3 motions beside one another, and the first 2 almost stop moving. That is the scale hidden inside a light year. Despite its name, a light year is not a measure of time. It is the distance light travels during 1 full orbit of Earth around the Sun. That distance is nearly 6 trillion miles. The number is so large that adding more digits would not make it easier to understand, so familiar speeds offer a better guide. A commercial airliner, somehow flying through space without stopping, would need well over 1 million years to cover the same route. Even a vehicle moving as fast as the International Space Station would still require tens of thousands of years. At those speeds, the crossing would not feel like travel in any ordinary human sense. It would feel like watching a clock hand move so slowly that entire civilizations could rise and disappear before it reached the next mark. 1 light year is only a small step in astronomy, yet it is longer than the full span of recorded human history multiplied many times over. Light does not move quickly merely because it has a powerful engine. Its speed is built into the relationship between space, time, cause, and information. A signal cannot carry news faster than light through empty space, and an object with mass cannot be accelerated all the way to that same speed. As more energy is added, the object can move closer to the limit, but the required energy rises without bound. This is why no ordinary machine can simply keep adding thrust until the universe gives way. Humanity first learned that light had a finite speed by noticing delays across the solar system, then refined that knowledge through increasingly precise measurements. The historical details matter less here than the conclusion they produced. Light has a speed, and that speed defines the largest distance nature can cross in a year. Every spacecraft follows behind. Far beyond the planets lies the uncertain outer region, known as the Oort cloud, pronounced Oort. It has never been seen as a sharp shell with a clear edge. Researchers infer its existence and possible reach from the behavior of long-period comets, and current estimates leave its outer boundary uncertain. Some models place parts of that distant population across a substantial fraction of a light year. That creates a strange reversal of scale. A probe could travel farther than any human-built object has ever gone, continue for thousands of years at present speeds, and still be moving through the Sun's remote gravitational neighborhood. Near the end of that route, the inner planets would no longer appear as separate worlds. The Sun would look like a bright point behind the spacecraft, no longer filling the sky with warmth or detail. Ahead would be darkness broken by stars that barely seemed to change position. The craft would pass through cold, thin space, where distances between objects were measured in years of light rather than miles. Nothing outside would suggest motion. Only the slow fading of the sun and the long delay of radio contact would reveal how far the machine had come. A road can become so long that a map stops being useful, and 1 light year crosses that threshold for present technology. It sounds like the first modest step toward the stars. For humanity today, it behaves more like an entire era. Near the Sun, the Parker Solar Probe moves faster than any other human-made object has ever traveled. During its closest passes, the spacecraft crosses an environment of crushing heat and intense radiation while solar gravity pulls it to extraordinary velocity. Its protective shield faces conditions no crude vehicle could endure, and its speed peaks only because the probe is falling deeply into the sun's gravitational well. If that peak velocity could somehow continue in a straight line, a single light year would still require roughly 1,500 years. That figure sounds almost encouraging, yet it rests on a false assumption. Parker does not carry an engine capable of sustaining that speed across interstellar space. Its record is closer to a sprinter reaching maximum pace on a steep downhill track than a traveler maintaining the same speed across an endless route. The probe accelerates near the sun, curves around it, and gives much of that geometry back as its orbit carries it away again. For a more honest picture of long-duration travel, Voyager 1 provides the better example. This spacecraft has spent nearly half a century moving outward, far beyond the major planets and into interstellar space. It now coasts at roughly 38,000 miles per hour relative to the Sun. Against a light year, however, Voyager's pace becomes almost motionless. At its present outward speed, the crossing would take roughly 17,000 years. That span reaches beyond any single society, language, government, or scientific tradition. The first cities, early writing systems, industrial machines, and modern electronics all appeared within a much shorter interval. A probe launched at Voyager's speed before the earliest known cities would still not have completed the route today. The comparison does not diminish the spacecraft. It reveals what the measuring stick does to every achievement placed against it. After decades of flight, Voyager has covered only a tiny part of the full interval. On a scale model where the route stretched across a long highway, the spacecraft would still be near the first marker after an entire human career of travel. There is no nearby world outside its window, and no bright destination waiting ahead. The sun has contracted into a powerful star behind it, while the planets have disappeared into the same small region of sky. Its instruments continue collecting information in an environment no operating spacecraft had reached before. Its radio remains connected to Earth by an increasingly weak signal, and the machine does not hurry. It endures. Pioneer and New Horizons confirm that Voyager is not an unusual failure of propulsion. They belong to the same broad family of deep space speeds when the comparison is expanded to 1 light year. Each can cross planetary distances, escape the sun's immediate neighborhood, and remain useful for years. None approaches the velocity required to turn interstellar travel into a human timescale mission. Gravity assists help explain both the strength and the limit of present methods. A spacecraft passing a moving planet can exchange momentum with it, changing direction and gaining speed without carrying all the necessary energy as onboard propellant. The maneuver is like stepping onto a moving walkway at precisely the right angle, borrowing a small part of its motion while redirecting your own. Within a planetary system, that technique can transform what a mission is able to reach. It can shorten flight times, reshape orbits, and allow a probe to visit several worlds with a limited fuel supply. Yet a planet offers only a bounded amount of useful motion, and the geometry must be available at the right place and time. Gravity assists cannot be repeated without limit, nor can they push a massive craft toward a meaningful share of light speed. The fastest machines humanity has built are not disappointments. They are remarkable instruments working inside a scale that does not reward effort with proportionate progress. Their success belongs to engineering. Their slowness belongs to the distance. A launch vehicle looks powerful because of the engines at its base, yet most of its towering body exists for one reason: to hold propellant. The payload occupies only a small fraction of the total structure. Every tank, pipe, pump, and support must lift the spacecraft and everything needed to keep accelerating it. That is where chemical propulsion begins to trap itself. Chemical rockets release energy from molecular bonds, enough for launch, orbit, lunar missions, and travel across much of the solar system. The technology is not crude or badly designed. It is operating near the practical ceiling of what chemical reactions can provide. Suppose engineers want more speed, so they add more propellant. The added supply makes the vehicle heavier. Now the engines require still more propellant to accelerate that extra weight, and the new supply adds weight of its own. The requirement compounds. It resembles a backpack that becomes heavier each time more supplies are packed inside, forcing the traveler to carry additional food merely to support the burden. The rocket equation describes this relationship with unforgiving precision. As the desired change in velocity rises, the required onboard load does not grow in a straight line. It grows exponentially. Doubling the velocity requirement can demand far more than twice the reaction mass, especially when the exhaust leaves the engine at a limited speed. Chemical exhaust cannot be expelled fast enough to push a useful payload toward a meaningful share of light speed. Staging helps because empty tanks and engines can be discarded once they have done their work. Each discarded stage removes dead weight, allowing the remaining craft to accelerate more efficiently. Yet staging does not remove the underlying limit. It only manages the mass problem more intelligently. An interstellar design also faces a difficulty that simple travel time estimates often hide. Reaching high speed is only half of a complete mission. A vehicle must accelerate, hold its course, correct errors, protect itself, and usually slow down at the destination. A craft that crosses the target region at extreme velocity without braking has completed a flyby. It has not arrived. The energy needed to decelerate can rival the energy used at departure, because the ship must remove almost the same motion it worked so hard to gain. Imagine a vessel that has accelerated for years and finally approaches the place it was built to study. The destination grows brighter ahead, and its instruments begin detecting the environment they were sent to examine. Yet much of the remaining engineering effort is devoted not to exploration, but to stopping before the target disappears behind it. Without a braking system, years of acceleration may produce only a few brief hours of useful observation. Carrying the reaction material for that slowdown makes the departure vehicle heavier from the beginning. That heavier starting vehicle demands bigger tanks, stronger structures, and still more stored energy. The problem folds back on itself. Simple calculations often divide distance by maximum speed and present the result as the mission duration. That figure may be useful initially, but it ignores acceleration time, braking distance, navigation power, and the protective systems surrounding the payload. The important question is no longer how fast an engine can move in isolation. It is where the energy originates, how efficiently it becomes thrust, what reaction mass must be carried, and how much useful spacecraft remains after propulsion is included. Serious interstellar proposals therefore look beyond a larger chemical rocket. Some use reactions with far greater energy density. Others leave the main energy source near Earth and transmit power to the vehicle from a distance. Some divide the craft into stages, while others try to avoid carrying conventional propellant at all. Each approach changes the balance, but none allows engineering to ignore momentum, onboard weight, or the cost of stopping. Chemical rockets opened the solar system because their strengths match planetary distances. A light year demands a different class of solution. Interstellar engineering begins when adding more fuel is no longer mistaken for solving the whole problem. Project Orion began with an idea that sounded almost too violent to be impractical. Instead of hiding a nuclear explosion inside an engine, the design placed repeated detonations behind a massive protective plate. Each pulse would strike the plate, and shock absorbers would turn that force into a controlled push. The spacecraft would survive not one blast, but thousands of them. Nuclear reactions release far more energy from a given amount of mass than chemical combustion, so the concept promised much higher exhaust velocity and thrust. With enough pulses, some interstellar versions were estimated to reach several percent of light speed. At that pace, crossing 1 light year could fall from thousands of years to a span measured in decades. The improvement was real in the calculations, yet the machine surrounding those calculations remained severe. A pusher plate would need to survive repeated shocks without cracking, warping, or losing alignment. Its dampers would have to smooth violent impulses into acceleration that the payload could endure. The vehicle would also be enormous because the nuclear devices, shielding, support structure, and control systems all added weight. Radiation would threaten the craft, the launch site, and any nearby environment. Treaties restricting nuclear testing created another obstacle, while political acceptance would remain difficult even if the engineering worked. Orion did not fail because its basic physics was meaningless. It failed to become practical because the price of using that physics was nearly as large as the vehicle itself. Several decades ago, Project Daedalus, pronounced Daedalus, approached the problem with fusion. The unmanned probe would ignite small fuel pellets in rapid succession while magnetic fields directed the resulting plasma backward to create thrust. In principle, the craft could accelerate to roughly 1/8 of light speed. A 1 light-year cruise at that velocity would take about 8 years before acceleration, braking, navigation, and other mission details were included. That was a remarkable reduction. It was also a paper design, not a spacecraft waiting for final assembly. The proposal depended on producing and storing large quantities of suitable fusion fuel. It required an ignition system capable of operating repeatedly for an extended period. its magnetic structures had to contain extreme heat while remaining light enough to accelerate with the rest of the probe. Every pulse had to occur at the right moment, with the exhaust directed accurately and the engine surviving the strain. Fusion research has made genuine progress in laboratories, but a laboratory experiment is not automatically a flight-ready propulsion system. A stationary facility can depend on heavy magnets, thick walls, large power supplies, and maintenance crews nearby. An interstellar engine must carry nearly everything it needs and continue operating far beyond immediate help. After acceleration, a fusion probe would enter a different kind of test. The engine would fall quiet, leaving the craft to cross years of darkness at a velocity no present mission approaches. There would be no service bay, no replacement parts arriving from Earth, and no safe place to stop if a pump, sensor, or control circuit failed. At such speed, reliability would become part of propulsion itself. A faster engine would mean little if the spacecraft could not survive long enough to use it. Antimatter stands even higher on the energy ladder. When matter meets antimatter, their mass can be converted into other forms of energy with an efficiency beyond chemical reactions and even fusion. On paper, that makes antimatter one of the most powerful possible fuels allowed by known physics. In practice, humanity produces only tiny quantities at enormous energy cost. Those particles cannot touch ordinary material without annihilating, so electromagnetic fields must hold them apart. The storage system would need to remain stable through launch, acceleration, vibration, radiation, and years of operation. A containment failure would not resemble an empty fuel tank. It would release the very energy the system was built to control. No human-scale antimatter engine exists, and no mission-sized reserve has ever been stored. Orion, Daedalus, and antimatter reveal the same pattern. Each step upward in possible speed requires deeper control of energy, heat, structure, materials, and containment. The flame becomes more powerful, but the machinery around it becomes harder to protect. Travel times can shrink from millennia to decades, or even years, inside a valid calculation. The distance between that calculation and a buildable machine can remain almost as formidable as the crossing itself. A reflective sheet can be so light that light itself begins to move it. Photons carry momentum, and their countless impacts can produce a small but continuous push. That is the principle behind a solar sail. Small missions have already shown that sunlight can alter a spacecraft's motion without burning onboard propellant. The sail keeps receiving momentum as long as light reaches its surface. Near the sun, that pressure can be useful, but it weakens rapidly as the beam spreads across greater distance. An interstellar design therefore needs something far more concentrated than ordinary sunlight. Breakthrough Starshot studies one possible answer: a vast, phased laser array on or near Earth. Thousands of emitters would have to behave as one instrument, aiming their combined energy at an exceptionally light, reflective sheet. For a short acceleration period, the beam would push a gram-scale craft toward roughly 1/5 of light speed. At that cruising velocity, 1 light-year corresponds to about 5 years of travel. The figure is striking, but it describes only a narrow kind of mission. The traveler would not be a crewed vessel, a large observatory, or a conventional deep space spacecraft. It would be closer to a flying instrument chip attached to an ultralight surface. The laser system would need extraordinary precision while the target moved farther away and the atmosphere distorted the beam. Aiming it would resemble threading a needle from a moving platform while the needle became smaller every second. The material must weigh almost nothing, remain stiff enough to hold its shape, and reflect nearly all incoming energy. If it absorbs too much light, it heats, deforms, and may fail during acceleration. It must also remain aligned while the beam pushes with an intensity no solar sail has experienced. A leaf can ride a steady breeze because the air surrounds it. This machine would depend on a narrow beam crossing a growing distance with almost no margin for error. Once the laser switched off, the craft would enter the longest and quietest phase of its mission. The bright source behind it would shrink, and the acceleration that made the crossing possible would be over. No repair crew could reach it. The vehicle would continue through darkness with only the power, protection, instruments, and intelligence engineers had fitted into a few grams. That small mass creates the concept's greatest strength and one of its deepest weaknesses. A lighter craft accelerates more easily, but it cannot carry thick shielding, large batteries, broad instruments, or extensive backup systems. A conventional spacecraft can survive some failures by switching to redundant hardware. A gram-scale machine may not have room for a second version of anything. Its tiny transmitter must also send useful information across an enormous separation with very limited power. Onboard systems may need to decide which observations matter most because only a small part of the collected data may reach Earth. Arrival creates another problem. The laser near Earth can accelerate the craft, but it cannot automatically slow it at a remote destination. Without braking, the vehicle would pass through the target region at tremendous speed and might have only hours to observe it. A high-speed flyby can still be scientifically valuable, but it is not the same as entering orbit or examining one place over time. Interstellar ramjets and warp drive ideas are sometimes offered as alternatives, yet they lie farther from practical construction. Ramjets face problems with sparse fuel and drag, while warp concepts depend on energy conditions unresolved in known physics. Laser sails occupy a different position. The push from photons is real, and the required speed does not clearly violate established law. The complete system, however, has never been built at the necessary scale. Every elegant part depends on another part working with extreme precision. The first machine to cross 1 light-year may look less like a ship than a carefully aimed fragment of technology. It may move so quickly only because almost everything normally associated with a spacecraft has been left behind. Inside a fast spacecraft, one clock travels with the crew while another remains on Earth. Both clocks work normally in their own surroundings. Neither one slows because of damage, gravity, or a faulty mechanism. Yet between departure and arrival, they do not record the same amount of time. This is time dilation, one of the central predictions of special relativity. It is not an illusion created by perception. It is a measurable difference produced by motion through spacetime. High-precision clocks have confirmed the effect, and fast-moving unstable particles survive longer than they would at rest because their internal time passes differently relative to observers on Earth. At ordinary speeds, the difference is far too small for a traveler to notice. As velocity approaches the speed of light, however, the separation between the two calendars grows. Consider a ship moving at 4/5 of light speed. From Earth's perspective, a 1 light-year cruise would last about 15 months. For the people aboard, the same interval would feel closer to 9 months, ignoring acceleration and braking. The gain is meaningful, but it is not magical. The crew saves months, not years, and the vessel still requires a propulsion system capable of reaching that velocity in the first place. Now push the example much closer to the limit. At 99% of light speed, Earth would still measure a little more than 1 year for the cruise. The travelers, however, would experience only several weeks. The two clocks have not disagreed about reality. They have followed different routes through space-time and arrived with different amounts of elapsed time. That is where relativity begins to sound like an escape from the problem. It is not. The closer a massive object moves toward light speed, the more energy each additional increase in velocity demands. No object with mass can be accelerated all the way to the limit. The final steps become harder, not easier. A mission also cannot jump instantly from rest to cruising speed. Human bodies, instruments, structures, and stored supplies can tolerate only limited acceleration. A comfortable crude design might need months or years to build velocity, depending on the engine and the acceleration chosen. The same process must occur in reverse at the destination if the craft intends to arrive rather than pass through. Those phases consume distance, energy, and time in both reference frames. Simple, constant speed examples are therefore teaching tools, not complete mission plans. Relativity also changes what the travelers see. Ahead of the vessel, familiar stars would appear compressed toward the direction of motion. Their light would shift in frequency, and some radiation would become more energetic. Behind the craft, other parts of the sky would dim and stretch away. The constellations known from Earth would lose their familiar shape. The forward view might resemble a narrow cone of concentrated light rather than an open field of evenly scattered stars. For the crew, that altered sky would be beautiful and dangerous at once. The same motion that shortens their experienced travel time would also intensify the radiation environment ahead. Meanwhile, Earth would continue aging according to its own calendar. People at home would wait through the full interval measured by mission control. Communication signals would still require time to cross the distance. Shielding would still add mass. The ship would still need power, repairs, food, and a way to slow down. Time dilation changes the traveler's experience of the route, but it does not reduce the amount of engineering required to create that experience. It offers no free propulsion and no hidden shortcut. It becomes useful only after a machine has already achieved the speed that makes it matter. Relativity can make time kinder to the crew. It cannot make the spacecraft easier to build. Empty space is not truly empty, and speed changes the meaning of everything inside it. At the velocities reached by present probes, the thin gas and dust between stars usually seem almost harmless. At a meaningful fraction of light speed, the same environment becomes a continuous engineering threat. A particle too small to see can strike with enough energy to damage the forward surface of a vehicle. The danger does not come from the amount of material ahead. It comes from the velocity of the collision. Beyond Earth's magnetic protection, radiation creates a different but equally persistent problem. Solar energetic particles are released during violent activity on the Sun and can expose equipment and crews to sudden bursts. Their influence weakens as a craft moves farther from the star. Galactic cosmic rays do not fade in the same way. They arrive from many directions after being accelerated by powerful events across the galaxy. Some carry enough energy to pass through ordinary shielding. Others strike the shielding itself and create secondary radiation inside the protected area. That makes the obvious solution less simple than it first appears. Adding more material can absorb part of the incoming radiation, but every added layer increases onboard weight. The propulsion system must accelerate that weight, support it, cool it, and later slow it down. A thicker wall may improve protection while making the entire mission harder to launch and control. Researchers have also studied active magnetic shielding. The idea is to surround the vehicle with a field that bends charged particles away, recreating part of the protection Earth receives from its magnetic environment. The concept is attractive because it could reduce dependence on heavy passive barriers. No complete lightweight system has yet demonstrated the field strength, geometry, reliability, and power supply required for a crewed interstellar craft. Radiation would arrive from many directions, but physical impacts would concentrate mainly at the front. Interstellar space contains sparse atoms, molecules, and dust grains rather than a perfect vacuum. At 1/5 of light speed, even a particle far lighter than a grain of sand can release energy comparable to a large conventional explosive when it strikes. The comparison does not mean every collision would destroy the mission. It shows how rapidly kinetic energy grows as relative velocity rises. A speck that would settle unnoticed on a table can become a serious impactor when the vehicle crosses the distance fast enough. One possible defense is a sacrificial forward shield designed to absorb damage before it reaches the main structure. Another is a layered impact barrier, sometimes called a Whipple shield. Its outer layer breaks an incoming particle into a spreading cloud, allowing deeper layers to distribute and absorb the remaining energy. Such protection works against small objects at current orbital speeds. A relativistic crossing would push the same principle into a far harsher regime. Engineers might combine several methods: multiple layers, replaceable sections, separated compartments, active detection, and duplicated control systems. Some proposals even consider clearing material from the route ahead, though no complete method has been proven across an interstellar distance. The uncertainty of local dust density adds another complication. A route may contain fewer dangerous particles than feared, or it may include regions where the risk rises sharply. Impact physics can be calculated, but the exact number and distribution of threats remain model-dependent. A tiny laser-driven probe and a crewed vessel would face very different tolerances. The small probe has almost no mass available for protection and may rely on numbers, sending many units while accepting that some will be lost. A human mission cannot treat destruction as an ordinary statistical outcome. Its defensive systems must protect air, water, food, electronics, living tissue, and every component needed for arrival. At the front of such a craft, a narrow boundary would take every blow. Outside, no sound would accompany the impacts. Inside, each strike could send heat, vibration, and stress through the structure. The shield would need to endure this for years while remaining aligned and intact. Every system behind it would depend on material only a short distance away from the next collision. The situation resembles a roof under nearly invisible hail, except the roof must also move at extraordinary speed and carry an entire mission beneath it. More protection means more weight. More weight means greater propulsion demands. Greater speed makes the impacts worse. The design becomes a balance where solving one danger strengthens another. Interstellar emptiness is not hostile in the ordinary sense. It has no intention, pressure wave, or visible storm. The vehicle creates the hazard by crossing sparse matter too quickly. At relativistic speed, emptiness becomes violent because the spacecraft brings the motion. Once the engines fall quiet, survival depends on ordinary tasks repeated without failure. Air must be cleaned, water recovered, food produced or stored, equipment repaired, and illness treated inside a sealed environment. For a mission lasting years, the spacecraft becomes less like a transport capsule and more like a remote settlement with no supply road. Water from breath, washing, and waste must be purified, while carbon dioxide is removed and oxygen restored. Current orbital life support equipment already recycles much of the water used by crews. That achievement is important, yet those systems still depend on cargo deliveries, replacement parts, and specialists on Earth. Interstellar distance removes all three. No fully closed human habitat has operated for many years without external support. Small losses that seem harmless during a short mission would compound across a longer one. A leaking seal, a weakening filter, or a poor harvest could gradually consume the margin between comfort and danger. Food is both a biological need and an engineering system. Plants can provide nutrition, recycle part of the air, and give the crew something living to care for. They also require light, water, nutrients, growing space, and protection from disease. Plants have been grown successfully in orbit, but supplying most of a crew's diet would demand a far larger and more reliable system. A failed harvest would not be an inconvenience. It could become a mission-threatening loss that cannot be replaced from Earth. The habitat would need stored reserves, overlapping food sources, and enough spare capacity to survive bad cycles. A pump may last for years, but the mission must be ready for the day it does not. Spare parts add mass, while manufacturing replacements on board requires tools, materials, power, and trained people. Redundancy protects the crew, yet every duplicated component makes the vehicle heavier. The human system is just as demanding as the mechanical one. Long confinement can affect sleep, mood, attention, judgment, and the way small disagreements develop. The problem is not simply boredom, it is the knowledge that privacy is limited, routine is unavoidable, and no one can leave after a conflict. A crew chosen for such a mission would need more than technical excellence. Its members would require emotional stability, patience, conflict resolution skills, and overlapping expertise. A physician might also need to repair equipment, while an engineer might need to grow food or assist during a medical emergency. No rescue team could arrive, and immediate advice from Earth would eventually become impossible. Some proposals consider induced torpor, a medically reduced metabolic state that could lower consumption and shorten the crew's conscious experience of travel. Safe long-term human torpor, however, has not been demonstrated. Muscle loss, bone loss, infection, circulation, and neurological effects would all need careful control. It cannot be treated as suspended animation or as a proven escape from confinement. Inside the habitat, most days would not feel dramatic. Artificial lights would rise on schedule. Pumps would hum behind the walls, while crops grew beneath carefully tuned lamps. Crew members would inspect seals, test air quality, exercise, clean equipment, and repeat maintenance routines performed hundreds of times before. Messages from home would arrive from an increasingly distant past. Birthdays, deaths, and changes on Earth might reach the ship long after they happened. Small rituals would matter because routine can preserve meaning as effectively as machinery preserves air. A shared meal, a scheduled conversation, or a view through a small window could keep the crew connected to one another and to the mission's purpose. The ship would have to protect not only human bodies, but motivation, trust, and sound judgment after years of confinement. A fast engine can shorten the crossing. It cannot make the habitat forgiving. The vehicle must carry life through space, repair itself when possible, and remain stable when people are tired, frightened, or divided. For the people inside it, the spacecraft would not merely be moving between worlds. For years at a time, it would be the only functioning world they had. An emergency message leaves the spacecraft and begins crossing the darkness toward Earth. It travels at the fastest speed nature allows. Even so, Mission Control will not receive it for an entire year. By the time anyone at home understands what happened, the crew may already have repaired the failure, changed course, or lost the ability to respond. A reply requires another year to return. One complete question and answer exchange therefore stretches across roughly 2 years. At that distance, ordinary mission control no longer exists. There can be no rapid conference with engineers, no live medical consultation, and no real-time command from Earth. The ship must continue while its request for help is still traveling through space. For months, the message would carry news of an emergency that no one at home yet knows has occurred. Inside the vessel, alarms might already be quiet again. When the answer finally arrived, it could belong to a situation that had vanished long before. A letter from one year cannot guide a crisis unfolding in another. This delay forces the spacecraft to become substantially autonomous. Its software must interpret sensors, identify failures, choose scientific priorities, adjust navigation, and protect essential systems without waiting for permission. The people aboard must do the same. They need enough authority and judgment to act when every instruction from Earth is already out of date. No training program can rehearse every possible breakdown across several years of flight. The craft therefore needs adaptable systems rather than only a fixed list of responses. Redundant hardware, diagnostic tools, and local repair capacity all become part of its basic resilience. Autonomy also changes the relationship between the crew and the people who launched them. Earth can offer advice and long-term planning, but it cannot truly intervene. Help becomes knowledge sent too late to function as rescue. The return trip creates an even larger commitment. A vehicle able to accelerate outward may not carry enough energy, reaction mass, or equipment to slow down, refuel, and repeat the process toward home. That does not mean every crude design must be one way. It means a return capability multiplies requirements that are already extreme. The destination would need usable resources, prepared infrastructure, or propulsion reserves carried from the beginning. Without them, departure from Earth could become a permanent separation from it. This is one reason serious near-term proposals favor uncrewed probes. A robotic craft avoids the mass of air, water, food, medical equipment, living space, and human radiation protection. It can be built in several copies, and a mission can accept a level of failure that would be morally impossible with people aboard. A small probe can accelerate more easily, though its limited power creates another problem. Its transmitter must aim across an enormous interval while sending a signal faint enough to disappear among natural radio noise. The onboard computer may need to select only the most valuable measurements and discard information that cannot be transmitted. Earth might receive not a complete record, but a carefully chosen fragment of what the probe observed. From the standpoint of efficiency, machines are the clearer first travelers. They need less mass, tolerate more risk, and can work without comfort or hope. The case for people rests somewhere else. Humans can improvise when instruments encounter something their designers never expected. They can connect observations, change priorities, repair unusual failures, and understand a place through direct presence rather than delayed data. That presence also carries cultural meaning that cannot be reduced to scientific output. Yet it comes at the price of making every system larger, heavier, safer, and more complex. The question is not whether humans add value, it is whether direct presence is worth multiplying every difficulty of the crossing. After crossing one full light year, the spacecraft would not arrive at another star. The Alpha Centauri system, pronounced AL First Centauri, lies more than 4 light-years from the Sun. The first successful crossing would therefore end in a region that appears almost empty. There would be no planet waiting, no new sun filling the windows, and no obvious destination to mark the achievement. The probe would simply be farther from home than any human-made object had ever traveled. That does not make the mission pointless. The space between stars contains thin gas, magnetic fields, energetic particles, and dust that shape the environment surrounding every stellar system. Most of what researchers know about this material comes from studying how distant light is absorbed, scattered, or shifted before it reaches telescopes. A probe inside that environment could measure it directly. It could count particles, map magnetic changes, record radiation, and examine the remote outer structure of the solar system from a position no observatory near Earth could reproduce. Remote astronomy reads a distant room through the light escaping its doorway. A spacecraft entering that room can measure the air around itself. The mission could also test estimates about the outer Oort cloud and the point where the Sun's remaining influence fades into the broader interstellar medium. Those boundaries are not clean lines drawn across space. They are changing regions defined by particles, gravity, magnetic fields, and the motion of the sun through the galaxy. The engineering required to reach them would begin producing value long before the probe completed the crossing. Lighter materials could improve missions throughout the solar system. More reliable autonomous software could guide spacecraft where communication delays already make direct control difficult. Better radiation protection could support crews traveling beyond Earth's magnetic shelter. Closed life support systems, efficient power supplies, stronger sails, and precise long-distance communication would all have nearer uses. Progress toward 1 light-year would not depend on a single invention appearing without warning. It would require propulsion, materials, navigation, energy storage, shielding, autonomy, and communication to mature together. A breakthrough in one area would not rescue a mission whose other systems remained fragile. No established law of physics clearly forbids an uncrewed probe from completing the route. No complete mission design currently solves every major requirement at once. The first crossing is therefore more likely to emerge from sustained work across generations than from one dramatic moment. Researchers may improve one component, pass the result forward, and never see the final machine leave. Others may inherit those systems, combine them with technologies that do not yet exist, and move the design another step closer. The effort would resemble a relay of knowledge in which the destination lies beyond the working life of many people carrying it forward. Someday, a probe may move beyond the distant reach of the familiar planets. The sun behind it will have narrowed into one star among many. Its instruments will sample material that humanity once knew only through faint traces in arriving light. Every correction will happen on board because instructions from Earth will belong to an increasingly distant past. When the probe sends its findings home, the signal will spread outward with little power to spare. It will cross the darkness for a year before reaching the people waiting for it. By then, the machine will already be farther away, continuing into a region no human artifact has entered. Nothing about the universe will have become smaller. The achievement will be that humanity finally built something capable of enduring its true scale.